Complex numbers. Polar form of a complex number. When a complex number is written in the form of z equals x plus yi, then it is said to be given in rectangular form. This complex number is represented by the point xy on an Argand diagram. So there is the point xy, or we could call it the complex number z, which is equal to x plus yi. So x on the real axis, y on the imaginary axis. The translation OZ, so from O to Z, from the origin to the complex number z, involves going a distance of x parallel to the real axis and a distance of y parallel to the imaginary axis. So, for example, we could go over and up, or we could go up and over to get to the complex number z. These are two sides of a rectangle as shown. So here we have our rectangle. The translation OZ can be described in another way by specifying two other quantities. The first one is the modulus or. The modulus is the distance from O, which is the origin, to Z. So from O to Z. So it's basically the radius of this circle. So or equals the modulus of z, which is the square root of x squared plus y squared. The second is the angle, or the argument theta. The angle theta is the angle between the positive side of the real axis and the translation OZ. So if we have a look at our Argand diagram, this is the real axis, this is the imaginary axis. And this is the positive part of the real axis. And this is our complex number z. So the argument of z is the angle that is formed with the positive part of the real axis and the complex number z. And we go in an anti-clockwise direction. So this angle here is the argument of z. The dominant convention is that we take theta to be between minus 180 degrees and 180 degrees, although other angles are allowed. This angle is sometimes called the argument and can be written as A or G Z. This means the argument of z. How the angle theta is calculated depends on which quadrant the point is in and will be investigated shortly. Once or and theta, so or being the distance from the origin to the complex number and theta being the angle or the argument, the translation OZ, i.e. the complex number z, is fully determined. The link between the two systems is as follows. So we know from trigonometry, from our SOHCAHTOA formula, that CAH stands for cos equals A over H, where A stands for the adjacent and H stands for the hypotenuse of a right angle triangle. So if this is our angle theta, then X is our A, Y is our O, it's opposite the angle, and or is our H, our hypotenuse. So using this, we have cos theta equals the adjacent, which is x, divided by the hypotenuse, which is or. And rearranging it to get the x in its own, we get x equals or cos theta. So x will always be equal to or cos theta when we're dealing with complex numbers. And likewise, our SO from SOHCAHTOA stands for sine equals opposite over hypotenuse. So our angle is theta, so sine of theta is the opposite, which is y, over the hypotenuse, which is or. So y over or equals sine theta. So solving for y, or rearranging to get the y in its own, we get y equals or sine theta. So y will always be equal to or sine theta. Then, if z is equal to x plus yi, z is also equal to or cos theta plus or sine theta, with an I stuck on. because remember the y is the imaginary part. So we swap the x for or cos theta, and we swap the y for or sine theta. And we can simplify this or factorize out the or. So z is equal to or, which remember is the modulus, multiplied by cos theta plus I sine theta. So z is equal to or cos theta plus I sine theta. Once or and theta have been calculated, so once the or and theta have been calculated, the complex number z equals x plus yi can be written directly in the form of z equals or cos theta plus I sine theta. This form of a complex number is called polar form. So we're changing from rectangular form, where we have an x and a y, or basically two real numbers, to z equals or cos theta plus I sine theta, which is our polar form. So this is our polar form, this is our rectangular form. Up until now we had only dealt with rectangular form. Sometimes instead of it being phrased as x plus yi, we've actually more so seen it as a plus bi. So a plus bi is rectangular form, or times cos theta plus I sine theta is polar form. Very common question in the Leaving Cert is to change between the two. Change from rectangular form to polar form, or change from polar form to rectangular form. Very, very common question in complex numbers. And this is specifically just for higher level. For much work done with complex numbers written in polar form, a convenient and much used abbreviation goes as follows. So or cos theta plus I sine theta can be shortened to or kis theta. So CIS. C standing for cos, IS standing for I sine. So or kis theta. This is very important to learn off, and it's going to come up a lot. Now that we have two ways of describing complex numbers, so polar form and rectangular form, it is necessary to be able to convert from one to the other. So let's start with converting from rectangular form to polar form. To convert a complex number from rectangular form to polar form, we draw a rough diagram. This is very important to draw this diagram. Or can be found using the definition of modulus, or by Pythagoras' theorem. In the first quadrant, theta can be calculated directly by using tan. In all other quadrants, we first calculate the acute angle to the nearest horizontal, so horizontal being the real axis. This angle, or, is called a reference angle, just as in trigonometry. However, there are different rules to follow. We then use or, the reference angle, to calculate theta. Example, express z equals 1 plus root 3i in polar form. So this is rectangular form, we want to change it to polar form, i.e. in the form of or cos theta plus I sine theta. The point which represents z, 1 root 3, is in the first quadrant. So if we imagine we have our four quadrants, so we have our real axis and our imaginary axis, this is the first quadrant. And we know that because 1 is the real part, which would be about here, and root 3 is the imaginary part, which would be about here. Both of those numbers are positive, so we know that we're in the first quadrant. So we plot a point thereabouts where we think it might be. We join a vertical line from z straight down to the real axis, and we join the point z, the complex number, with the origin. We're forming a right-angled triangle, where the modulus is actually the hypotenuse of our triangle, a right-angled triangle, and we can also call it or, because technically it's the radius of our circle. So we have a distance of 1, which is going to be the adjacent. We have a height of root 3, which is going to be the opposite. It's opposite the angle. And we have a hypotenuse of or. So this is the complex number z, which is 1 comma root 3. So we can calculate theta directly here. We can calculate theta. So or is going to be the square root of 1 squared plus root 3 squared. So this is Pythagoras' theorem. So it's the square root of the adjacent plus the square root of the opposite added together. And we get root 4, which is 2. So the radius of our circle, or the hypotenuse of our triangle, is 2. So since we're in the first quadrant, we can use tan. So we know from SOHCAHTOA, we have TOA, so T is equal to O over A, the opposite over the adjacent. So tan theta is going to be equal to root 3 over 1, which is root 3. And into the calculator, we get theta to be 60 degrees, or using rad mode, pi over 3. Thus, or cos theta plus I sine theta is going to be 2 cos 60 degrees plus I sine 60 degrees. Or kis theta is going to be 2 kis 60 degrees. Or in radians, z is equal to 2 cos pi over 3 plus I sine pi over 3, which is equal to 2 kis pi over 3. Express z equals minus 3 plus 3i in the form of or cos theta plus I sine theta. The point representing z minus 3, 3, which lies in the second quadrant. So this is our first quadrant, this is our second quadrant. So we go across to minus 3 on the real axis and up to positive 3 on the imaginary axis, and we plot our point. Then we draw our triangle, we draw our diagram, so a line straight down, and we draw in the hypotenuse of the triangle, so we join the complex number to the origin. This is just a rough diagram, by the way. Draw a diagram indicating the lengths of the sides of the triangle, no minus numbers. This is important because length and distance can never be negative. So although this is minus 3 on the real axis, this distance or this length is actually 3. So the adjacent of our triangle is 3 and the height of our triangle is 3, or the opposite. And we're going to try and work out what the hypotenuse is. Show the reference angle or. So if we work out the angle inside this triangle, we're actually getting the reference angle. But remember, theta is the argument. So if this is the positive part of the real axis, then this angle here is theta. But we're going to use the reference angle to work this out. So theta can be found by subtracting or the reference angle from 180 degrees, because this forms a straight line. So if we work out the reference angle, we just subtract it from 180 degrees to get theta. So or equals the square root of 3 squared plus 3 squared. So 3 squared plus 3 squared, which is the square root of 18, which is 3 root 3. So we use Pythagoras' theorem to work out the hypotenuse of the triangle, which is or. Then we use TOA from SOHCAHTOA. So tan is equal to opposite over adjacent. The opposite is 3, the adjacent is 3. So tan of or, the reference angle, is 3 over 3, which is 1. So tan of 1 is 45 degrees. So our reference angle is 45 degrees. So this angle here is 45 degrees. So this angle, theta, what we're looking for, is 180 minus 45 degrees, which is 135 degrees. Hence, or cos theta plus I sine theta is equal to or kis theta. So z is equal to 3 root 2, because that's or, cos 135 degrees, because that's theta, plus I sine 135 degrees. Or we can simplify as z is equal to 3 root 2 kis 135 degrees. Express z, 2 root 3 minus 2i in the form of or cos theta plus I sine theta, where theta is in radians. So z is represented by the point 2 root 3 minus 2, which lies in the fourth quadrant. So this is the fourth quadrant, and 2 root 3 is about here, and minus 2 is about here on the imaginary axis. So we plot our point z, and remember that the sides of our triangle must be positive. So we have 2 root 3 for the adjacent, we have 2 for the opposite, and we're going to try and work out the hypotenuse. In the fourth quadrant, we can take the angle theta to be negative. This you will need to learn off by heart. The angle theta will be negative in the fourth quadrant. Calculate the reference angle or first. So we calculate this angle OR using Pythagoras' theorem. So we have OR equals 2 root 3 squared plus 2 squared, which is root 16, which is 4. So the hypotenuse of the triangle is 4. Then theta is equal to minus OR. Don't forget to write the angle in radians. So again, we use TOA. So tan is equal to the opposite over the adjacent. The opposite is 2, the adjacent is 2 root 3. So tan of OR is 2 over 2 root 3, which is 1 over root 3. So OR is going to be pi over 6. So make sure that your calculator is in rad mode to get radians. That's the same thing as 30 degrees. Thus theta is minus pi over 6 because we're in the fourth quadrant. So for the fourth quadrant, you just change your angle, your reference angle, to a minus. Hence, or cos theta plus I sine theta is going to be 4 cos minus pi over 6 plus I sine minus pi over 6. So or kis theta is 4 kis minus pi over 6. Express z minus 4i in polar form. The point minus 4, which represents z, lies in the third quadrant. Here's our third quadrant now. And here we have minus 4 on the real axis and minus 4 on the imaginary axis. So we plot our point z. In this quadrant, we also take the angle to be negative between minus 90 degrees and minus 180 degrees. We calculate the reference angle of OR. So again, we use Pythagoras' theorem. So this is our angle OR. This is our opposite 4. This is our adjacent 4. And we want to start off by working out the hypotenuse. So again, we use Pythagoras' theorem. The square root of 4 squared plus 4 squared is the square root of 32, which is 4 root 2. So the hypotenuse of a right angle triangle is 4 root 2. So again, we use TOA, which is tan equals opposite over adjacent. The opposite is 4, the adjacent is 4. So tan of OR, the reference angle is 4 over 4, which is 1. So the reference angle is 45 degrees. So if our reference angle had been in the second quadrant, which is just above where our actual complex number is. So if our complex number had been in this quadrant here, all we would have done was taken our angle away from 180 degrees because we have a straight line. So we do have to do that. We take 45 away from 180 degrees, but we also then have to make it negative because it is below the real axis. So anything below the real axis we turn negative. So we end up with minus 135 degrees. Hence, or cos theta plus I sine theta is going to be 4 root 2 cos minus 135 degrees plus I sine minus 135 degrees. So summarizing, or kis theta is 4 root 2 kis minus 135 degrees. So to summarize, we always start measuring our angle from the positive part of the real axis and we move anti-clockwise. So if we're in the first quadrant, the reference angle is just equal to theta. We don't have to do anything to it. We just use TOA. We just use tan. If it's in the second quadrant, we subtract the reference angle from 180 degrees. Now, if it's below the real axis, we basically apply the same rules as the first and second quadrant, but we just make them into a minus. So if it's in the third quadrant, we still do 180 degrees minus the reference angle, but then we subtract, we add a minus. And if it's in the fourth quadrant, it's just going to be whatever the reference angle is, but add on a minus. So if it's above the real axis, it's positive. If it's below the real axis, it's negative. It's important to note that these are different rules for the reference angles in trigonometry. So just a reminder, in trigonometry, in the first quadrant, the reference angle is equal to the angle, which is actually the same as complex numbers. In the second quadrant, it's actually the same again. You subtract from 180 degrees. But the third quadrant and fourth quadrant are different. So third quadrant, we minus 180 degrees. And fourth quadrant, we take the angle, angle away from 360 degrees because we have a full circle. So it's important to note the differences between complex numbers and general trigonometry. If a complex number is purely real or purely imaginary, then the point which represents the complex number will lie on one of the axes. In this case, or is the positive distance from the origin to the point, and the angle theta is shown opposite. So if it lies on the positive part of the real axis, theta is 0 degrees. If it lies on the positive part of the imaginary axis, theta is 90 degrees, because we can see it's a right angle, because remember we're always going from the real axis anti-clockwise. If it lies on the negative part of the real axis, theta is 180 degrees, so going from here across to here we've got 180 degrees, a straight line. And if it lies on the negative part of the imaginary axis, theta is minus 90 degrees. So it's as if we're starting at the positive part of the real axis, but we're going backwards. So it ends up being minus 90 degrees. Express z equals minus 4 in the form of or cos theta plus I sine theta. Notice there's no imaginary part. Z is represented by the point minus 4, 0, which lies on the negative side of the real axis. So this is the real axis, this is the imaginary axis, this is minus 4. So this is Z. It lies on the negative part of the real axis. So or is just going to be 4. The distance from the origin to the complex number Z is 4 units. So it's not minus 4 because distance must be positive. Theta is 180 degrees. We go from the positive part of the real axis all the way around. We form a straight line which is 180 degrees. Hence, or cos theta plus I sine theta is going to be 4 cos 180 degrees plus I sine 180 degrees. Or to summarise, or kis theta is equal to 4 kis 180 degrees. Most scientific calculators can convert complex numbers from rectangular form to polar form. Because different makes and models work very differently, you should learn how your calculator performs this conversion. For example, to convert z equals minus 1 minus root 3i to polar form using a Casio FX83 calculator, we clear the calculator and then press Shift plus minus in brackets 1, Shift bracket minus in brackets root 3, the right arrow, bracket, equals. And we will see on the display or equals 2, theta equals minus 120. And then you substitute this into or kis theta. Note that your calculator has been programmed to use the standard international convention that theta is between minus 180 degrees and positive 180 degrees. Also note that if or works out to be a decimal, we can always square it to find or squared, and so write or as a surd. So to convert z equals something plus minus something I to polar form, shift plus the real part, shift bracket, the imaginary part, the right arrow, bracket equals. And the POL stands for polar. Polar form to rectangular form. To convert a complex number given in polar form to rectangular form, we simply evaluate the trig functions and tidy up. So this is much quicker and easier than going from rectangular to polar. We always tend to use exact values, i.e. no decimals unless specifically instructed. Angles outside minus 180 degrees and 180 degrees can occur in calculations. Express in the form x plus yi. So z equals 4 cos 135 degrees plus I sine 135 degrees. So z equals 4 cos 135 degrees plus I sine 135 degrees. So into the calculator, making sure you're using degree mode, cos 135 degrees is minus 1 over root 2. And again into the calculator, using degree mode, sine 135 degrees is 1 over root 2. Don't forget you've got your 4 in front. Then we multiply in the 4. 4 times minus 1 over root 2 is minus 4 over root 2. And 4 times I, 1 over root 2, is 4 over root 2i. And then simplifying, we get minus 2 root 2 plus 2 root 2i. Express z equals root 2 cos 405 degrees plus I sine 405 degrees in the form x plus yi. So z equals root 2 cos 405 degrees plus I sine 405 degrees. Into the calculator, in degree mode, cos 405 degrees gives us 1 over root 2. Sine 405 degrees gives us 1 over root 2. Then we multiply in the root 2. Root 2 by 1 over root 2 is 1. And root 2 by I, 1 over root 2, is 1, which is just I. So we have our real part and our imaginary part, our real part and our imaginary part.